There you go.
Welcome back, everybody. Happy Monday.
NASA's Lucy mission is going to be the first mission to explore the Trojan asteroids. These are asteroids that live in two swarms, one that's ahead of Jupiter and another that's behind Jupiter. And we want to go and look at these building blocks of the planets, the ones that didn't get accumulated into the planets, to really learn about the evolution of our solar system.
Lagrange points are these stable regions of space. They're around pretty much every planet in the solar system. Jupiter, by virtue of being the largest planet in the solar system, it also has the biggest Lagrange points. And these are little stable reservoirs where asteroids get in, but they never come out. In reality, what we have is sort of a snapshot of what the solar system looked like billions of years ago.
Early in the solar system, the giant planets were migrating outward, away from the sun. And at one point, there was chaos in the solar system. Some small bodies were ejected out of the solar system. Others could have been trapped in these Lagrange points. And that's one theory for how the Trojan asteroids came to be where they are today.
My job as a mission architect here at Lockheed Martin, it's very interesting, and it sort of encompasses the biggest picture of the mission. What is the trajectory? What sort of propulsion do you need to fly that trajectory? What does the spacecraft look like? So in the case of, for example, Lucy, it's like, okay, it's going out 5 times further from the sun than the Earth is. And so it's going to need big, huge solar arrays just because of that.
Lucy has 3 scientific instruments on board the spacecraft, and we'll also be using 2 of the spacecraft subsystems to contribute to the science investigation. With the LORRI instrument, we'll be able to get panchromatic images, which will tell us about the geology, and the crater history, which gives us the age of the surface. With the TESS instrument, we'll be able to measure the temperature of the surface at different points. And with the RALPH instrument, we'll be able to measure the composition of the surfaces. The Jupiter Trojans, they have a variety of surface characteristics. They have different colors and different surface compositions, and that leads us to believe that maybe they formed somewhere else. In choosing the Lucy targets, we wanted to be able to compare different objects that have different surface properties, but a very similar orbit. Lucy will visit 1 main belt asteroid and 7 Trojan asteroids.
I don't think there's been a single NASA mission that will have visited as many objects on separate orbits in the solar system as the Lucy mission will. We launch in October of 2021. That trajectory just basically does a 1-year loop around the sun and comes back to Earth in October of 2022. And that will slingshot us out now onto a trajectory that takes a little more than 2 years to come back to the Earth. Now we're moving a whole lot faster than we were. We get that trajectory set up, and that second Earth gravity assist takes that velocity and redirects it in the direction we want. That'll take us out to the Trojan space.
On our way out to the L4 swarm of the Trojans, we're going to visit a main belt asteroid. That main belt asteroid is named Donald Johanson, after the discoverer of the Lucy fossil. We named the Lucy mission in honor of the Lucy fossil because we learned so much about hominid development and evolution from that fossil, just like we're going to learn about the solar system evolution from the Lucy mission.
From there, we take a couple of years off and we continue to cruise up until we get to August 2027. And there we encounter our first Trojan asteroid. It's called Eurybates. It's the product of a huge collision that happened millions and millions of years ago. Something big hit it and just blew it apart. And so Eurybates is the biggest chunk of that cataclysmic impact. And it's a C-class asteroid, which is kind of interesting because there's a lot of C-class asteroids in the main belt. There's very few of them in Trojan space. So that's one of the mysteries we're going to get at is, okay, why is Eurybates so different? As we've studied it and tried to refine its orbit, we've discovered it's got a little moon. And so we're going to try to get pictures of that too as we fly by. And about a month later, in September of 2027, we're encountering our second Trojan asteroid, Ptolemy. So it's one of the smaller objects. We're flying by at about 6-7 kilometers per second. We have to take pictures like crazy as we fly by, but we're not stopping at any of these. We come to our next object, Lucas. It's wash, rinse, repeat. And so we snap pictures like crazy at Lucas. And then about 7 months after that, we do the exact same thing at another object called Orus. And that's the last L4 swarm object that we're going to be visiting. And from there, we start dropping down back into the inner solar system now. So we were out past Jupiter's orbit a little ways. Now we're falling back in towards the Earth. So the trajectory is sort of set up to sort of return back to Earth for free. And we use that to redirect the trajectory now towards our final Trojan asteroid. And so this is an object out in the L5 swarm. So it's trailing Jupiter by about 60 degrees. It's a roughly equal mass binary system called Patroclus and Menetius. You can imagine it's sort of like this dumbbell in space. So imagine a great big dumbbell spinning around, but there's no bar there. It's just the objects orbiting each other. It's a very rare thing to find in the inner solar system. However, if you look out past the orbit of Pluto, equal mass binaries are kind of common out there. Another clue is like, okay, are these objects in the Trojan swarm, are they maybe related to the Kuiper Belt objects out there past Jupiter? And if they are, this will be amazing. We can go and visit Kuiper Belt objects by just going out to Jupiter.
We really have never seen Trojan asteroids up close before, and we want to understand their geology. Look at the craters on this surface to understand the history of their surfaces, understand the composition of their surfaces so that we can maybe learn something about where they formed. And all of those will be clues to help us understand how the solar system evolved.
Well, hello, everybody. It's Scott Roberts of Explore Scientific and the Explore Alliance, and this is the 35th episode of How Do You Know? Today, Dr. Barth joins us to talk about Lagrange points and what did they mean and how do they determine them? So let me add you on. Daniel Barth, how are you, man?
Hey, doing good, Scott. Hi, everybody. Welcome back to How Do You Know? And this is our second program on the James Webb Space Telescope. But this time we're not focusing on the telescope itself, but rather today we're going to take a look at the Lagrange points. And it gets a lot of press. Oh, the Webb is orbiting at L2 or orbiting around L2. And people are like, what the heck is L2? And clever people, oh, that's a Lagrange point. And that's kind of, it's almost a false sense of knowledge. And people, my students will drill down on it. Yeah, but okay, but what is it? Why is it there? Is it a place? Is it a thing? How are they made? And so we're going to take a look at some of these mysteries today, Scott, because
Okay.
the Lagrange points are really quite fascinating. And they have not only a long and rich history in mathematics and astronomy, but of course, they have a rich history in science fiction as well. The science fiction community has long used the idea of Lagrange points and space stations and colonies and things located in the Lagrange points. And actually, we knew about Lagrange points before we knew how they worked. The asteroids they were discussing, the sometimes called the Trojan asteroids, although that's not quite correct. The asteroids that precede and follow Jupiter in orbit. These asteroids were discovered early in the 1800s, and people were looking at them and going, why are they there? And some of these things inspired Mr. Lagrange, and they say Lagrange, I say Lagrange. He is a man of many aliases, Scott. He's a man of many aliases. It turns out people say, "Oh,
so
he's
am
an
by the way. But I can't say them on the air. So
if you told me, you'd have to kill me." People say, "Oh, well, he was an Italian." Well, not really quite. He was born in 1736 in the city of Turin, which is now in Italy, but at that time was the Kingdom of Sardinia. Much like Nicholas Copernicus, who is claimed by Poland, but in fact, at the time, that was the Principality of Worms. And so it wasn't part of Poland until much after his death. So he was born Giuseppe Ludovico Lagrange. And I'm probably massacring that. And so if we have Italian speaking viewers out there, my apologies. But he was born and given an Italian name. And this young man was going to the University of Turin, which again is now part of Italy, to study law. His father wanted him to become an attorney. And while he was there at university, like many of us, he encountered great books and great minds. And one of the things he found, Scott, was Edmund Halley's description of Halley's Comet.
Okay.
And this led him to the works of Newton, including the Principia. And so at the age of 17, this young man decides, no law career for me. I'm going to study mathematics and astronomy. And we don't know exactly why he did it this way, why he didn't take regular courses in mathematics, but we do know that essentially all of his mathematics was self-taught. So this is a young man who hasn't studied really mathematics significantly until he hits 17. Then with the works of Newton and Halley and a few other people, Euler, he basically goes ahead and studies mathematics for a year. And at the end of the year, he's writing papers and he's writing to Euler and he's writing to other great minds of the day. And he gets an appointment as an assistant professor of mathematics at 18. And so you think of this, how much time have you spent studying mathematics, professor? Oh, well, I picked it up last year. I'm really a law student, but it was just kind of fun. It turns out that he was quite a poor teacher, but a very brilliant theorist. I flatter myself to say I'm kind of the other way around. I'm not so great as a theorist, but I'm a pretty good teacher. And so at this point, he's writing to Euler, who's a German mathematician. And Euler is very, very impressed with the young man. And he recommends him to his patron, Frederick the Great of Germany. And Frederick the Great invites him to come live in Germany and become a member of the Berlin Academy of Science and Mathematics. Wow. And this at, 18. And so he moves to Berlin. And like many people who immigrate, there are great millions of people who come to the United States and kind of anglicize their names. The pronunciation of my name is anglicized. Barth is an Americanization. It's not the German Bavarian pronunciation of Barth that my grandfather would have used. And many people come to a country and they adjust their name so native speakers can say it. And so Lagrange did this. And then later on, after Frederick the Great dies and his young wife dies tragically, Louis XVI invites him to come to France and be part of the French Academy of Sciences and to have access to the Paris Observatory. And so he moves to Paris and he changes his name again, this time to Joseph-Louis Lagrange. And he was probably known as Yusuf or something similar in Germany. But this is a guy who a man of many aliases. And basically all he's doing is every time he gets a new patron, he changes his name to reflect the language of the people who are paying him. So not uncommon. We see this in immigrant communities around the world. And people who say, well, my name is this, but my friends call me George or whatever. We see this all the time. In fact, you talk about George, the planet George, Uranus, discovered by Herschel, who was German at the time. A German was on the throne of Britain, and he came to Britain and he's discovered the new planet. Let's name it George after my patron. Galileo discovers the moons of Jupiter. Let's call them the Medicean satellites or the Medicean stars. And so this sort of flattery, if you will, of the people who are paying the bills was very common in the 17th and 18th century. And Lagrange went ahead and participated in this. So what did he do? Among other things, Scott, he's known as the father of the metric system. He's in France during the time of the French Revolution, and he transfers his allegiance from Louis to the revolutionaries. And he helps them develop the metric system. And his brilliant idea is, oh, if all the measurements are base 10, it's so easy to go ahead and multiply and divide and change units. And the French revolutionists adopted this idea. They loved the idea of throwing out the old imperial measurement system. They brought in the metric system. You may remember for a while, there was a metric clock with, instead of 12 hours for a half a day, it was 10, and each minute had 100 seconds. And so they had a metric clock.
I do not remember that.
They never got so far, at least I don't think so, as a metric calendar with just 10 months in it. But we still have and enjoy the metric system today. He also wrote the book Analytical Mechanics, which is a treatise of pure mathematics. Also, it's one of the first textbooks that weaves together mathematics and physics in a digestible way. Anybody who's ever, people say, oh, the Principia. And of course, Copernicus is great on the revolutions, and Galileo's plays, right? The dialogue of the two chief world systems. But these books that came before Lagrange, really experts only. I'm sure you've browsed through the Principia, haven't you, Scott?
Yes.
It's a monster.
Yeah.
It's just a monster. Between the notation, which we don't use Newton's notation anymore, we use Leibniz's notation, Newton's methods, Leibniz's notations. But Newton's strange notation to most modern eyes in his language, and his very, very long, complex geometric arguments to prove ideas in mathematical calculus. And the Principia is a monster. I own a copy, many people do, but it's awful to try to read. Lagrange's book was used as a standard text for many, many, many decades, more than a century, because it was readable. And he wasn't a great teacher, but he was a great mathematician and theorist and writer. The other thing is, Lagrange is one of the first people to extend Newton's ideas. Newton has these lovely ideas in the calculus, and he worked out the orbit of the moon. And he did the calculus of gravitation, the idea that every gravitational body can be thought of as a pinpoint mass. But Lagrange looks out, and with the eye of an astronomer and the mind of a mathematician, he sees things like the Trojan asteroids, and he realizes, there's a problem here, because you look at Newton, and Newton says, you can't solve a three-body problem. And we're talking about the idea that three bodies, and two smaller bodies or two similar sized bodies in orbit around a third larger central mass, it isn't stable. If you go ahead and look at trinary systems, you tend to have situations where two orbit very closely and one is very far out. So it's orbiting essentially around the common barycenter of the two inner stars. But three-body systems are notoriously unstable, and no one has yet come up with a universal system to the three-body problem the way we have one for solving quadratic equations and that sort of thing. But Lagrange came up and he said, there are some special cases where the three-body problem works as long as you have a large object, say a star, a medium-sized object, say a planet, and then a relatively quite insignificantly small object, such as an asteroid. And Lagrange figured out that there are 5 unique points where essentially everything becomes stable. And we think about stability, and we can think about stability. Think about two teams engaged in tug of war, right? High school picnic sort of competition. And so you have two equally matched teams, and they both are tugging on a rope. And for a while, the person drops the flag and says, go. And for a while, everyone's grunting and straining, but nobody's moving.
Right.
The forces are balanced. And the forces pulling right, the forces pulling left that are tensioning the rope are the same. And so the rope doesn't go anywhere. When we think about this idea, we can also think, Lagrange realized, we can think of the idea, and I'm going to make sure that I don't lose anything here. I'm putting this in, there we go. It's now in the field of view with the camera. And so I've got all this, as Scott would say, it's a metal ring on the end of a string. And so I'm swinging this around, trying hard not to biff myself in the nose here. And if we think about this, what we realize, this is a pretty exact analog for orbital motion, because as the ring moves around, and you think about this, which direction is the string pulling? The string is always being pulled towards the center. The string represents what we call a centripetal or center-seeking force. Gravity provides this function out in space. And so we have moons orbiting planets, planets orbiting stars. Gravity provides that center-seeking force that keeps the body in orbit. But why doesn't the Earth just fall into the sun? Why doesn't the moon? There's currently a very bad science fiction movie called Moonfall. Have you heard of this one? It's out right now.
What is it called?
The idea is suddenly the moon decides to fall to Earth. Well, if that happens, we're screwed. Put your head between your knees, kiss your butt goodbye, because there's no saving anyone.
No saving.
It's going to be a very bad day, friends and neighbors.
I'm getting out my telescope though.
That's right.
That happens.
Yes, I would spend my last days observing, and it would be quite fascinating. But the question, why doesn't the moon fall? If the Earth is pulling on it gravitationally, why doesn't it fall? And it's the same reason why, although I'm pulling the string in toward the center all the time, why doesn't the ring fly into my hand? And the answer is this rotational motion creates an outward or centrifugal, center fleeing force.
Mm-hmm.
All of us who've been on a teacup ride, what's the great one when we were kids? You ever go on the octopus, right?
Mm-hmm. Sure.
At the county
there was
fair.
One that you're like inside this giant.
Right, it's got the arms out, and the little cars outside can whip around.
The floor would drop, and you would.
Yeah, the floor drops out.
Yeah.
Certainly that impossible ride where you stand against the wall and the floor drops and you're stuck to the wall.
Yeah, and then they tilt it like that, and you're going.
That's
around.
right, and you're whipping around. Absolutely, loads of fun. This is a centrifugal force, and I used to love to go on rides like this when I was a kid. I'm not sure I would enjoy them anymore, but I love them as
They're
a
not
young
even
boy.
legal anymore. So
Are they really?
I
Well, that's sad.
I don't know. I mean, there's a lot of rules these days.
It's been
Rides.
a long time since I went to a county fair. But these rides, centrifugal force, the center fleeing force, the outward flinging force from rotational motion. And so we think about the moon and we realize, we have this outward flinging force, the centrifugal force created by the moon's velocity as it orbits the Earth. And we have the inward or center seeking force. And that's what we get from gravitation. And of course, it was Robert Hooke, Newton's arch rival, who came to the society and said, I can prove that all you need is a center seeking force and lateral motion or momentum. And he took a pendulum bob and he went like this and gave it a push. And he says, there you go, momentum and a center seeking force, because any pendulum will swing over the point of its suspension if it's just released. And he said, there you go. That's how orbits are created. Newton couldn't figure out how to explain it or demonstrate it for the life of him. And this is now called Hooke's pendulum. So you get all these great people, brilliant minds working on these things at the time. But Lagrange is the first fellow to realize there's more than one way to do this, and you can do it with 3 bodies, not just 2. And so we think about, what are these Lagrange points? They are always in the orbital plane. So if you think about the moon going around the Earth, that makes an orbital plane. The Earth going around the sun, the galactic plane. There's always an orbital plane. Lagrange points are always in this plane. And at these points, Scott, because the force is balanced, it's like the tug of war. If you put your hand on the rope in the tug of war and the 2 teams are straining and the rope isn't moving, there's no force either direction on your hand. Your hand can just sit there. A bird could come and perch on the rope and just sit there perfectly still. Nothing would happen, because the 2 forces outward are balanced. So there's no force on the bird perching on the tug of war rope. This is the same thing in a Lagrange point. All the forces cancel. Some of them are gravitational. Some of them are centrifugal from rotary motion. And these things balance out, so the net force is 0. And if the net force is 0, as Newton said, an object at rest remains at rest unless an outside net force acts on it. And in these places, there is no net force. And so the object doesn't go anywhere. It stays perfectly stable. And that's an interesting thing to say, but it's not exactly an interesting thing to visualize. So we're going to go ahead and share a screen today, and we're going to take a look at some things. There we are.
And when you get a chance, Daniel, there's a couple of questions here. So,
oh, sure. Do you want, should I take them now? Might as well.
Might as well. Okay. So Jim, watching on YouTube, wants to know, do other planets in our solar system have Lagrange points?
They all do.
They all do.
The larger the planet is, the larger the state. Lagrange point isn't a point, it's a region. Jim, it's a region, it's an area. The more massive the planet, the more massive and larger area the Lagrange point covers. Mathematically, yes, there's one point, but it's an area of stability. Jim, if you think about, we've talked about this before, if you think about gravitation, the old rubber sheet in the bowling ball, trampoline, and a person standing on it, and the trampoline curves in where the weight is placed on it. The Lagrange point is this kind of a low point, right? It's a place where if you had these low points in a trampoline, if you had a couple people standing on it and rolled marbles across, the marbles would tend to roll toward the people because that's where the fabric is stretched, and that's where the low or stable points are. Space and gravitation, much the same. And so just if you think about a person standing on a trampoline and creating a depressed region, this is much like a Lagrange point. Yes, the person's weight may be at one point, but the effects on space-time are spread over a region. And so the bigger the guy on the trampoline, the bigger the region of depressed fabric. It's the same thing with space-time. So if you talk about Jupiter, a massive planet, 312 times the mass of the Earth, it has very large Lagrange points. If you talk about Pluto, which is very tiny, those Lagrange points would be very small. And Pluto's Lagrange points are so small, it would have problems holding on to things bigger than a baseball, I think. I don't know the exact numbers on that, but Jupiter manages to hold large full-size asteroids. Pluto would not. Earth has a Lagrange point moonlet. It's quite small. It's 1 kilometer or 2 in diameter. And it's not stable. We think it's going to hang around for 4,000 or 5,000 years and then get flung out in a way. Other planets can, as the Earth comes into alignment with Mars or Jupiter or outer planets, they can tug and disturb things. So stuff in a Lagrange point, the smaller the planet is, the less stable the Lagrange point is. The larger the planet, stability is much longer. And we say, oh, the Trojan asteroids are permanent. But as we've talked about before, Scott, very, very little in the solar system is actually
Permanent.
permanent in a cosmic lifetime of the universe sense.
That's right.
So here we see, is there another question? I love that
There
one,
were
Jim.
a
That was
couple of
great one.
questions, but I think you actually answered them already.
Oh, good. Okay.
Peck on YouTube says, does the mass of the object make any difference on the L point? And
Yes.
Harold Locke wants to know, also watching on YouTube, how about a different point for each set of the masses?
A different point for each set of masses.
Yeah, and I think he's just saying, you know, if there's
The Lagrange points are actually, if you think about a primary and a secondary body, planet, moon, star, planet,
Yeah.
whichever. You think about primary and secondary body, the primary body's in effectively a circular orbit or pretty close to, or even in a fairly extreme elliptical orbit. The Lagrange points are defined by the two primary bodies. Little things can inhabit the Lagrange points in a stable relationship, but the Lagrange points themselves are created by the primary and secondary bodies alone.
Okay.
So
Right, and
the
then we
Earth and the
have-
Moon alone create five, everything has 5 Lagrange points. The Earth and Moon create 5, and there are things inhabiting those regions. But the little asteroids in the Trojan points don't create the Lagrange points at all. They just live there.
I see. So,
Okay.
so Sydney, watching from Japan, says, if there are stationary areas in space, how do they fit in the universe being in an, in an expanding universe?
Okay, well, when we talk about an expanding universe, we're talking about kilometers per second per megaparsec. The Hubble constant is in terms of very, very large volumes of space. And when you talk about the relatively small volume of just a solar system, and this kind of puts some perspective to it, our solar system is a light day wide, roughly. And when we talk about a parsec, which is 3 1/3 light years, so you're talking about 1,000th. Our solar system is 1,000th of a parsec, and we talk about the Hubble constant in terms of megaparsecs. The expansion of the universe really doesn't affect us on solar system scales at all in anything like we are expanding and stretching. Yes, we are. We have no instruments which would be capable of measuring that. We generally measure the Hubble constant in terms of the motion of galaxy clusters, very distant indeed. And when we talk about stable, not stationary, but stable places, the L points for Jupiter, Earth, anything, they orbit around the sun with the planet. It's a relationship between the planet and the sun that makes the L point, but because it's a relationship between those two, as the Earth orbits around the sun, the L points move with it. And that's why we put spacecraft there, because they are in this low, stable place, and it takes very little fuel to stay there, and they are dragged around the sun by the Earth rather than by rocket power. And so that's why we can put something like Webb up at L2 and expect decades of service from it,
Right.
because its main motion to keep station, right? Station keeping, the idea of staying in formation with the Earth and Moon. If you're going to pick a random point and force a satellite or a space station to stay in a particular relationship with the Earth and Moon, you'd be expending a lot of rocket power to do it. The L points let you do it for free. All you have to do is minor, tiny little corrections now and then. Mostly what the Webb's fuel is going to be used for is steering, maneuvering,
I see.
which
It doesn't need a
takes
lot.
very little energy.
Yeah. Yeah. Okay. And then another question from
Sure.
Armando Lee, watching from the Philippines. He wants to know, are there galactic Lagrange points as well?
You know what? I'm sure there are. You think about the Large Magellanic Cloud, right? Dwarf galaxy orbiting our galaxy. You have our central galactic mass. And remember, Newton says you don't have to consider the size or shape of a planet, you can effectively deal with it as a point mass located in one place. So the massive center of our galaxy is going to be where the Sagittarius A star black hole, the supermassive black hole at the center of our galaxy is. And the Magellanic Clouds have their own. They too would have Lagrange points. Now, are there star systems? I think that was, if somebody out there is an astronomy, astrophysics student and looking for a lovely, lovely project, I think going to search for star systems that are trapped in the Lagrange points for the Large Magellanic Cloud would be a killer project. I see a PhD in your future. I think that would be a brilliant thing. You would need access to some pretty phenomenal equipment. You're not talking amateur equipment here, folks. You're not going to take your 8-inch Schmidt cast or your, I have a 20-inch Dobsonian. That's not going to slice it. You're going to need access to something like Cerro Tololo, Keck, the Canary Islands scope, the large radio array. You're going to need access to something pretty phenomenal to see this. But I suspect there are, in fact, star systems in the L4 and L5 points for the Magellanic Clouds. The other points, I really kind of doubt it. And we'll talk about why as we talk about specifics for Lagrange points here in a minute.
All right. And I have a couple more, but I'm going to let you go on and then
okay.
we'll come back to
I'm
those
so
questions.
thrilled we're getting all these great questions.
Yeah, there's questions.
This is awesome. And people from Japan, the Philippines, and
Yes.
I think
All over the
Pekka
world.
is somewhere in the Netherlands, is he not?
Pekka's in Stockholm.
Stockholm.
Stockholm,
Sweden. There you go. Sorry.
Yep.
Because he's an old friend and a longtime viewer. But yeah, we're getting great, all these questions from around the world.
Yeah, that's cool.
So take a look at our little diagram here. And this basically shows you what we talked about earlier. How does a planet stay in stable orbit around the sun? And we see here that there are two balanced forces, the centrifugal or center fleeing force from rotary motion, we've colored red here, and the centripetal force of gravity. And whether you're talking moon and earth or earth and sun makes no difference. Basically, the two forces balance. And this is why, Scott, if we want to go to a higher orbit around the Earth, we have to expend more rocket energy. We have to fly at a faster rate because more kinetic energy will cause our orbit to expand. And when we get too close to the Earth with a satellite, hello, Elon Musk, I'm talking to you and your Starlink satellites. He lost 40 satellites just recently because a solar storm thickened up the exosphere around the Earth, and it created more drag. And guess what? They lost kinetic energy and they spiraled in and they burnt up. And so when we talk about gaining kinetic energy makes our orbit bigger, losing kinetic energy makes it smaller, but it always reaches a stability at any speed where centripetal and centrifugal, the inward and outward forces are balanced. And that's the way geostationary satellites work. You just get to an orbit. It's about 26,000 miles high or 40,000 kilometers roughly. And at that point, the centrifugal and centripetal balance when the orbital period is 24 hours. We know the space station, the ISS, goes around in about 90 minutes, give or take, but very far out. The orbits, there's more kinetic energy, but the orbit takes a longer time because the circle is much bigger. And we get these lovely geostationary satellites, which gives us weather satellites.
Yes.
And other things. So there you go. So no force on the orbiting moon because centripetal and centrifugal cancel out. This is what the L3 point looks like. The L3 is exactly opposite. And this is a stable trope of science fiction. The mysterious Earth 2, which orbited in our orbit, but at the opposite side of the sun. And it would always pace us around the orbit so we could never see it because it was behind the sun. And this was a science fiction theme. Many, many authors have used this. And that's where L3 would be over here. When we take a look L1, and we've got L1 here, and we realize, gee, we've got L1, and we realize that, gosh, L1 is between the Earth and the Moon. Jules Verne, when he wrote the book From the Earth to the Moon, 1890 something, he wrote that, in fact, the astronauts only experienced weightlessness at the L1 point. He said, if you're on this side, closer to the Earth, you'd still feel the Earth's gravity holding you. If you were beyond the L1 point, you would flip the ship over and the moon's gravity would provide for you. Fritz Lang's great film, Frau im Mond, Woman in the Moon, deals with exactly this idea that Verne brought up. Verne and Lang were both wrong, because in free fall, there is no local gravity. This is why in the space station, the astronauts are weightless. But at this particular point, at an L1 point, you don't have to expend a lot of energy to stay there. If you could park there, and again, we have put satellites in L1, but L1 is not very stable, Scott, because as we know, the moon is in an elliptical orbit. The moon both speeds up and slows down. We know about supermoon and mini moon, right? We
Right.
talk about that as astronomers. So as the moon comes closer, we get supermoon. It appears larger in our field of vision as it goes farther away. And because the moon wobbles in and out and speeds up and slows down, it takes, you would have to have either a very small object. If you have something as big as a decent sized satellite, you have to expend some energy to stay at L1. And L1, too close to Earth for Webb. Earth not only emits a great deal of energy, thermal, radio, visible light, but it's too close. And you think about where these two balance out, it's fairly close to the moon. It's about 7/8 of the way to the moon. But at this point, you're still nothing in the way of all this energy from the Earth, and it's not a great place for the Webb Observatory.
So, Daniel, is
Sure.
the moon's orbit decaying, or is it expanding?
expanding.
It's expanding.
And friends, if you go back to the How Do You Know show archives,
Okay.
there was an episode on the Roche effect and the doomed moons of Mars. And we talk
right.
about there how the Roche effect, one of the things that happens, either there's a Roche limit. If you're inside the Roche limit, your orbit is decaying. The planet is stealing, because of the interaction of the tides, the planet's stealing energy from the moon. Its orbit decays and it spirals in. If you're outside the Roche limit, which our moon is, our Earth's Roche limit is only about 60,000 kilometers away. The moon is about 380 kilometers away, 1,000 kilometers away. And so our moon is well outside the Roche limit. And because of that, the Earth is giving rotational energy. Our rotational period slows down. The moon's orbital speed picks up and its orbit expands. It's not very fast, about a centimeter per year. The moon's orbit expands at about the rate your fingernails grow or your hair grows. Some of us, our hair grows. But the moon's orbit is not stable over cosmic time, but certainly over human lifetimes. Oh, sure. It's not going anywhere. Hollywood notwithstanding. So that's our L1 point. Here's our L2 point. And I'm going to separate these out a little bit physically so I can just show one on the page. There we go. So here's our L2 point. And at this point, this is where Webb is. At this point, we have an inward gravitational tug from both the Earth and the moon. You can see our two green arrows here, Scott, the centripetal forces, and of course the moon's.
Yeah.
Only about 1% of the mass of the Earth, but it's a lot closer to L2 than Earth is. And so we have these two centripetal forces, or inward pulling forces. And then because of the rotary motion, L2 follows Earth around. It basically, L2 orbits the Earth in the same period as the moon does, right? Because the Earth and moon together create L2. So as the moon orbits, L2 orbits at the same speed. And so at the L2 point, the centrifugal force is as big as these two gravitational pulls added together. And so once again, the forces balance. We are at L2. This is not to scale, friends. The moon is about 250,000 miles. L2 is about 1 million miles. So about 4 Earth-Moon distances. So about 4 times the Earth-Moon distance. So if this were to scale, our L2 point would actually be off the screen here. And this point does provide Webb with a small amount of shielding. It's inside the moon's penumbra. And so it does reduce some of the radiation. The distance does a lot more, Scott, because if you talk about the difference between L1 and L2, L2 is about 6 times farther away than L1 is. And so it gets about 1/36. That's that inverse square rule. And so Webb receives a lot less radiation from the Earth. Basically, at this point, all Webb's really worried about is the radiation from the sun. And because L2 is still effectively at 1 AU away from the sun, it gets the same amount of solar energy per square meter, about 1 watt per square meter, that the Earth's surface does. And that's why it has that fabulous 5-layer shield. You know, I just had a great idea, Scott. We should invent this and put it on the Explore store. I want a JWST umbrella with 5 layers stretched out. So you open it up and it's a 5-layer umbrella.
I want one that just fits on like a hat, you know. So
right, like with the band and the little umbrella with 5 layers.
Wear at science festivals and such, you know. Couple of more questions.
Sure.
Pekka in Stockholm says, isn't there a lot of dark matter around galaxies? And do you think that affects the L points?
No, because the L points are created by concentrations of mass in orbit around a massive primary body. Dark matter exists, and this is going by Vera Rubin's ideas. We also did a How Do You Know on this. Dark matter exists as a spherical halo. So since it's not concentrated at one point, it doesn't have that 2-point relationship that creates the Lagrange points. So no.
Right. Okay. And then Jim's Astro is asking, how difficult is it to put a satellite in the L2 point?
You know, we know where it is quite precisely. And the feat of astrogation is not that terrifically hard. Look at the little video clip we had before. Oh, we're going to go around the Earth once. We're going to slingshot around. We're going to go past the Earth and slingshot twice. We're going to go out to the Trojan point, and then we're going to come back in and slingshot past the Earth the 3rd time, and we're going to reverse direction. So now we're heading anti-orbital, and we're going through the Greek point, the L5, and it's like, holy cow. Compared to that, putting Webb in an L point where you just flew out there and reached a stable, not that difficult compared to some of the absolutely amazing features of astrogation. Friends, the movie The Martian, right? The movie The Martian. And it has this lovely section where this guy says, I am a steely-eyed missile man. And he comes up and he says, no, remember that scene in the movie where he says, oh, here's a stapler and this is the space station, comes around, and he uses he uses the NASA director as the Earth and the other person.
Oh, right.
Mars.
Yeah.
And he shows how And that was a really fantastic act of astrogation compared to those sorts of things, which NASA does routinely and ESA does routinely now. Popping a satellite into L2 is not hard at all.
Yeah. Done
So-
all the time.
Right. So let's go ahead and take a look. Here's L4 and L5. And we take a look at L4 and L5, and this is the one people really have difficulty understanding. So we think about this. I've drawn green arrows here as gravitational forces. And of course, when we think about the moon versus the Earth, the gravitational force from the Earth is much greater, and the moon is here pulling a little bit, but basically what happens is these two come out at an angle, and this is classic vector addition. And people are going to look at my drawing and say, Doc, those vectors won't sum to zero. Gotcha. We're looking at limitation in my drawing and illustrating skills. But basically those three vectors, the outward centrifugal force, and then the gravitational acceleration from the Earth and the moon create these stable points. And there's one 60 degrees behind and one 60 degrees in advance. And the one behind are known as the Trojan point asteroids. L4, the preceding ones, are known as Greek point asteroids. And in the tradition of early 18th and 19th century astronomy, where they were using a lot of Greek names, oh my gosh, there's all these asteroids clustered in these areas. How do we name them? And so they went to the Iliad, Homer's great epic poem about the Trojan War, where there's a cast of thousands. And they said, okay, everybody in this area is going to be named after somebody on the Greek side, like Achilles. And the Trojans are named after other people. And I'm struggling to pull up Menelaus, I think, is one of the Trojan kings. Anyway, so they had basically the characters and they named them. And I don't know if they've run out of characters now or not. But there's a Trojan point. If this is Earth and Moon, Earth has a little satellite. I believe it's in the L4 point. And again, I said it's a kilometer or two wide. It's it's big if it's going to hit you. As far as asteroids go, it's relatively minor. So if it was dragged out of the L point and fell in toward the Earth, if it hit the moon, a 2 or 3 kilometer asteroid might kill people on Earth because an awful lot of material would be ejected out of moon's gravitational pull, and the nearest big gravity well is us. And you could potentially, if you had a 2 or 3 kilometer impactor striking the moon, you could get rocks that were house-sized or SUV-sized landing, which could easily kill people. A dinosaur killer type impact with a 10-kilometer asteroid that created a crater like Tycho would absolutely kill people on the Earth, and for many years to come.
A lot of people don't think about that, that they worry about the potentially hazardous objects, the PHOs out there, but we all think about those things hitting Earth, okay? No one
Moon
thinks about
protects
the
us,
scenario of a
maybe.
giant one hitting the moon and the blast back, causing havoc.
A new Tycho-sized crater or Clavius-sized crater on the moon's near side, that would be a fabulous event. And I would be out watching with my telescope.
Me too. I'm going to be out.
I would be out,
We'll be out there.
with my,
I'll bring all my
pennant and my big #1 finger, and I would be screaming woohoo and taking pictures. But you have to realize this isn't going to be a winning story for everybody on Earth.
You have to share them on Facebook quick. Yeah.
Sure. A question from Facebook?
No. I said we're going to have to be sharing those images on Facebook.
Oh, yes, we would. Oh my gosh.
quickly.
So
Anyhow, I know it's
say, why
morbid,
didn't we put it at L4, L5? Well, the proximity to Earth and Moon creates a more stable. We talked about that trampoline analogy before, where the bigger guy makes a bigger dent in the trampoline. Closer to the Earth and Moon, the bigger dent right? It's a more stable space. L4 and L5 are not as stable. It would take more fuel to sustain an orbit there. So that's why they selected L2. L1 over here on the opposite side is really not stable at all, because other bodies out here, it's very far away from the Earth and the moon, and it just doesn't have the extra stability. These other L2 and L3 points are the most stable, and we tend to see L4 and L5. It would be interesting to see if there were asteroids in the L2 and L3 point for Jupiter. L4 and L5 can be quite stable, but
Yeah.
it takes a lot more gas to get out that. You're talking 60 degrees in advance of the Earth's orbit. More expensive to fly out that far,
Sure.
and a longer lag
Might be
time.
able to fly into it, you know, some debris out there.
Correct. And here's your, this is courtesy NASA. And this is a lovely diagram showing, and I love this because the L4 and L5 points, you can see how it makes basically an equilateral triangle.
Mhm.
And the geometry works out very beautifully. And L1 and L2, the most stable. L3 is the least. L4 and L5. The advantage of L4 and L5, of course, is that they're not orbiting the Earth, right? They're just in Earth's orbit. So the difference there. And I suspect that's why asteroids settle here. Now, people are going to say, have I done all the astrogation and astrophysics of this? No, I have not. I understand this in a general physics sense. I understand this. But if you ask me, have I done the math like Joseph-Louis? No, sorry. He was in the honors class above me in school. So I'm an enthusiastic astronomer and educator, but I make no claims to being one of these folks like the astrogators for NASA and ESA. The guy who was yesterday and saying, "Oh, we're going to loop around a second time, third time, fly out here, fly out there." My jaw is just hitting the floor. Even to come up with this, and then the hours and hours and hours of supercomputer time to confirm such a flight plan. Oh my gosh, I'm just I bow to his mad skills. What a magnificent imagination and intellect that fellow has. Just stunning, stunning. So, a few last questions. Do we have any more, Scott, as we wrap up here?
There's just comments of, that, others, if we were witnessing a large impactors coming into Earth, that they would get their scopes out and watch it with us. So
I would.
we're there with you, man. So, astronomers to the end.
I'm sure you remember the impactor, the Russian meteor. And I'm drawing a blank on the name of the city. Chelyabinsk. The Chelyabinsk meteor.
Yeah, with all the
2013
dash cams getting the
dash cams getting it, and the security cameras of windows being blown out, and all sorts of crazy stuff.
That was
and at the time I was just, the videos were popping up on the internet. I spent a couple of days just showing all my students these videos. And somebody said, well, how much time was there between seeing the light in the clouds and the boom? And I said, oh, several minutes. You're talking, this is 50, 60 miles high. And somebody said, if you saw the flash and the cloud, would you go out and watch? And I said, oh, yes. I said, I would put my safety goggles on. I said, I would duct tape my phone to the wall and start the video camera. And I would want to be like the guy in the Maxell commercial with his tie being blown behind him. I said, I would love that. And somebody said, well, what if you got hurt? And I went to Shakespeare. And each year upon the day, the men who were here with me shall strip their sleeves and show their scars and say, these I had on Crispin's day with Harry the King. This story shall the good man teach his son. Yes. And yes, if I went out, if I saw that and I had the video of myself being blown away And if I got cut, I'd say, yeah, that's the great meteor of Northwest Arkansas of 2022. And I was there. Oh my God, it would be thrilling. Just
That's right.
don't give me, I don't want a softball sized rock giving me a crease in the head that I can't
I
recover
don't know.
from.
I think if I have, well, when I go, I mean, what a more amazing way to go. You know, you're
I
watching
would
it.
tell
come
my
right in,
relatives
and
to show
boom,
that
that's
video
it.
clip at my
Okay.
funeral.
So
Give me a Viking funeral and show that video clip
Arr.
waving a screen on the river's edge. Here he goes, bam! There goes Grandpa.
that's it.
I would-
Yeah,
I would-
just
I would
leave
be
it
all
in.
in.
Just leave it in. Bury me with it. You know. So
Bury me with a chunk. Go find
That's
a
right.
chunk and bury me with it. Absolutely.
that's right.
I'm
That's
going to
right.
hold it.
Let's see. We do have more questions and comments here. The dad frequency wants to know, and I'm not familiar with this, the Younger Dryas event. Was that
Okay.
frags of a moon impact?
There's speculation about that. And there's talk that younger. I'm thinking there's another one which was a continental unzipping where the Pangea was breaking up, and I'm not all up on my various extinction events.
These things happen before we were born, right?
Oh yeah, even you and me, Scott.
Wow.
So Younger Dryas.
That was a long time ago.
Younger Dryas. Let's. I'm not even sure. how you-
12,000, between 12,900 and 11,600 years ago.
Yeah. There's a couple of them. There's one that dates about that time, and they've just been finding evidence in ice cores that there was a gigantic solar flare. It would have made the 1859 solar event, which started fires along telegraph lines. It'd make that look like peanuts. And they find this because there are certain isotopes of barium and chlorine, which these huge amounts of plasma impacting the Earth's atmosphere create, and then they get deposited on the ice and they show up in ice cores in Antarctica and the Arctic. And Younger Dryas event was a human bottleneck. There was a huge decrease in the human population. I think if I've got this right, about 10 to 12,000 years ago, human population on the Earth dropped to about 10 to 15,000 individuals. There was a great famine, and some people suspect that it may have been a huge asteroid impact, which would have created a nuclear winter, which would have created global famine. No one's found, to my knowledge, though, a smoking gun crater, the way we have with Chicxulub and the dinosaur killer event from 65 million years ago. And you would think only 10,000 years ago, you realize meteor crater is 50 to 60,000 years old. You would think if Younger Dryas was indeed an impact, of course, it could have been at sea, but you would think even at sea, the sea is only a couple miles deep on average. And if you're talking about that kind of an impact, or you would think that surveys of the seafloor would show a crater or a crater remnant. But to my knowledge, nobody's come up with one. So more investigation is called for, one of those great mysteries. Somebody's PhD and Nobel Prize may be lurking there.
Yes, that's right. Jim's Astro comments, just amazing. I have a much better understanding of Lagrange points. So thank you very much, Dr.
You
Barth.
know, that's what we look for here. And I've had people ask me, why do you do that? Your comment from Jim's Astro is exactly why we do this.
Oh, yeah.
It's exactly why.
Sydney wants to know out of Japan. He says, are there concerns about micro meteors hitting the mirrors? I'm sure he's talking about Jay West.
Yes. But again, when we talk about that far out, the moon will deflect some. And the heat shield is designed with ripstop features so that if meteors puncture, but again, we've talked about this before too, Scott. There was a madman who went to the McDonald's Observatory and emptied a loaded revolver into the mirror.
Yes.
and they lost, 6 .45 caliber slugs, bang, bang. And then he tried to shoot the observatory supervisor. Truly an insane person, but they
Yes.
lost less than 1% of the mirror's surface area, and they just filled it with pitch and painted it black. People with Dobsonian telescopes, often older ones, have chips and flaws in the mirror, and they simply paint them black. It doesn't really, this thing is gigantic, 6.5 meters. Go ahead and get a 3.25 meter long string, which is going to be what? About 10 feet, something like that, 10 or 11 feet. And go and chalk that circle in your driveway or on a blacktop parking lot. And then go
Right.
ahead and take some paintballs and shoot into it, or take the little round, the little stickers, and put them, a few of them on the ground. You know what? You're not, certainly a large meteor could take out the whole observatory,
Sure.
but micrometeors, nah, we're not really worried about it. I doubt you would be able to tell the difference 20 years from now, because Hubble's mirror is exposed. And it's 30 years on, and certainly it must have. Nobody's gone up to examine it in decades, but certainly if we did that, and I think it would be a wonderful thing to do, to go up, capture it, and bring it back at some point.
Oh, yeah.
Nobody's going to pay for that in Congress, kids, just saying. But to bring it back and to have it on display and to examine the wear and tear, because certainly in closer Earth orbit, it gets a lot more junk, because the Earth is kind of like a magnet attracting these things in. And at L2, you're much farther away. The Earth and Moon both draw things away from you rather than towards you, like they would with Hubble.
Let's see. Harold Locke says it's better to laugh in the face of certain death than to cower. Yes.
I agree.
We're with you, Howard.
I agree. Absolutely.
That's
true.
right, Harold. Let's see. Yeah, Harold, everybody's agreeing that you had excellent explanations today.
Oh, good.
And Armando says Chelyabinsk was spectacular, and I would be proud showing a scar I sustained from the meteor fall shockwave. Me too. It's got to be better than any tattoo you could get, right?
I would think.
Come on.
I would
that's cool.
get Chelyabinsk tattooed
That's
around
right. Yeah,
it.
you see that? You see this? Meteors. That's
Yeah,
right.
that's right.
I survived it. Let's see. Armando says, thank you, Dr. Barth, for a comprehensive yet easy to understand lecture about Lagrange points. Billy's Astro says, thank you for today's show, Dr. Barth. Yes, better understanding of Lagrange points.
Y'all are very kind.
And Amanda Z, who's, I think she's new, but perhaps she's been watching some other programs. Thanks for another great discussion. Have a wonderful evening, everybody. Michael Montgomery, the L points are moving at rotational velocities. So at a minimum, J West or any other object going to an L point must reach orbital velocity to get to point. And the gravitation maintains the speed. And the gravitation maintains the speed. I guess that's the question.
Yes, it's a matter of the kinetic energy. It's the same for any satellite, Scott. We put satellites in orbit, and it doesn't matter if they're in low Earth or high Earth orbit or out by L2. They're orbiting the Earth. The moon is orbiting the Earth, and the moon's position is maintained by its orbital velocity and kinetic energy. And with Webb, it's the same. Of course, if you want to put a satellite in orbit, you have to direct that energy properly. You have to steer it. It's like merging onto a freeway. We get on a ramp at 20 miles an hour and we hit 65 by the time we merge with traffic. That's the kinetic energy that keeps us safe because we're moving at the speed of traffic. With any satellite, not just the Webb, any satellite at all. Mm-hmm. We boost it up and we merge into the lane we want by hitting the correct speed. And that's it precisely.
Well, that's great. Daniel, thank you so much
Very
for a
welcome.
great program and a great explanation.
And thank you to the audience today for all the questions. You guys make the show great. You really do.
yeah, that's right. Very nice comments overall and interesting questions for sure. Tomorrow we will have more Open Go-To Community with Jerry Hubble, and we have the 84th Global Star Party. So stay tuned for more programming, and we will see you tomorrow. And until that time, keep looking up. Take care.
Thanks, everybody. Bye-bye now.
Bye-bye.